Please get ready with a pen and paper. So let's move on to the first question. From the above, determine which of the given curves correspond to the highest path loss exponent among the considered cases. Basically, you need to find which is the highest path loss exponent.
Remember three and
Yeah. So N5.
five.
Right. So N5 is the highest path loss exponent. Consider the following statements. First statement is low RSSI and high SINR is an unlikely scenario. Second statement is high RSSI and low SINR implies a bad channel scenario. Which of these statements are true?
But even though we have high RSSI, high SINR is a very important criteria for a good channel.
Right. So, both the statements are true. High, how is SINR and RSSI related? Basically, RSSI is the received signal power, but SINR tells us the quality of your received signal. So, if SINR is low, it implies a bad channel, even though your RSSI is high. And having low received signal strength and high SINR is it's like that scenario is not possible. So, it's an unlikely scenario. Is it okay?
Oh, okay. Contradicting, right? The RSSI, which includes noise as well as interference.
Yeah.
Thank you.
Okay. For hexagonal geometry, which is a valid cluster size? Okay. So can I equal to 2 and j equal to 2 give us 12?
Yeah, two. Okay. Four.
Yeah,
Four.
4
Oh,
plus.
yeah.
Yeah. So valid cluster size includes 12 as well. 7 and 12 is again valid. Basically should satisfy I square plus ij plus j square to be an integer. We can write n is equal to 12 when I is equal to 2 and j is equal to 2. So 12 is a valid cluster size. Is anybody having any doubt in this question? Okay, so we are moving on to the next question. Which one of the following methods can be used to improve the carrier power to interference power ratio in an interference limited system? We need to improve the carrier to interference ratio, power ratio. Okay. What do you mean by intra-cell handover? Can anybody?
That is due to sectorization, right?
Right. So if like between sectors of the same cell, we could do a handover. So that also helps us to improve the carrier to interference ratio. In the sense, if in one sector we're going to have more interference, then we could give a handover to improve the C to I ratio. And sectorization definitely it's going to help us. If you're having say a sector antenna like this, then to the point, to this red point, only these three cells base stations might give us more interference. So we will be getting rid of the right side three. So sectorization is going to help us, and intra-cell handover is also going to help us, because if we are going to face a poor C to I ratio, then we could have a handover, intra-cell handover. Again, frequency hopping is also going to help us. If we're going to have an interference for frequency f1, then we could switch over to frequency f2. So to improve carrier to interference power ratio, we can use sectorization, intra-cell handover as well as frequency hopping. Okay, the next question. This problem is about finding the path loss exponent of a single breakpoint path loss model. You have the average receive power readings given here for different distances. What is the difference between the measured receive power in dBm and the estimated receive power at 400 meters? We know the expression for a single breakpoint path loss model. So PR is equal to PT minus 10 log 10 of 4 pi d by lambda the whole square into d by d break the whole power n. We know, actually, we have the measured receive powers that's given. So estimated receive power we could find. We know that the d break is given as 100 meters. If we just substitute that, we are going to get minus 6n. And the measured is given as minus 15. So minus 15 minus 6n, we'll get minus 15 plus 6n. For the above problem, basically with this tabular column, using the least squares method, estimate the path loss exponent. Let us see how to solve this. The objective function or the cost function is going to be pi minus pi cap the whole square. Sum of pi minus pi cap the whole square. We've taken the d break distance to be 100 meters. So the estimated powers in terms of for the different p's, we'll have to find that. For the first one, we already found it to be minus 6n pi cap. For the second, it is minus 10n. For the third, it is minus 13n. Then what do? We try to write j of n. So after finding j of n, we need to find that n that minimizes the cost function. So we have to differentiate j of n with respect to n and equate it to 0 to get what is n. So n is 4.43 for us. Is the approach okay? Do you have any doubts?
Or the otherwise, we can substitute all these options A, B, C, D, and for which that function is minimum, and that is the correct answer. Maybe
That also you could do. But the actual procedure when you're asked to do least squares method and find the estimated path loss, this is the way to do it. And moving on to the next question. Consider a cellular system with hexagonal cells and a cluster size of 3. If a 120-degree sectorization is employed in a system, how many tier 1 interferers will be present in the worst case scenario? Try to construct a cell structure with cluster size 3 and then assume that we are going to do 120-degree sectorization. Now, can you guys find how many tier 1 interferers we might have for a worst case scenario?
I think 2. Yeah, 2. I think if it is full sectorization, it is 3. 120, 2, I guess.
Sectorization, in the sense, if it's 120-degree sectorization, one second. So
120-degree sectorization.
if we're going to have
3 sectors inside one cell.
Yeah, right. So it's something like this.
So tier 1, I think it will be 2, ma'am. Sorry.
Okay. So what I think is it will be 3.
Tier 1.
Let's imagine that P is our point in the corner of the cell, which might experience worst case. In that sense, if it's 120-degree, this C2, C1 and C6 might not cause us any problem. But we'll have the impact of C5, C4 and C3.
Yes, ma'am.
Okay, so this is the next question. In a normalized UV coordinate system, consider 2 points. Point A is 3, minus 3 and point B is 3, 3. What's the actual distance between points A and B if length of each side of the hexagon is 1.2 kilometers? So actual R is 1.2 kilometers. First of all, how do we get the normalized UV coordinate system is that in a cell structure system like this, when we keep R is 1 by root 3, we get the distance between two centers as 1 meters or 1. So that is the reason why we move on to a UV coordinate system, right? The distance between the points in a UV coordinate system is root of u1 minus u2 the whole square plus v1 minus v2 the whole square plus u1 minus u2 into v1 minus v2. To find the actual distance, it is the distance measure into r root 3. Let's move on to the next question. If a signal to interference ratio of at least 10 dB is required for a satisfactory forward channel performance of a cellular system, what is the cluster size that is to be used for a maximum capacity if the path loss exponent is equal to 3.8? We are taking that we have 6 co-channel cells in the first year and all of them are at same distance from the mobile. What we have to find is the cluster size that should be used for maximum capacity when n is equal to 3.8. What is given is SIR. So how do we proceed with this? Here we might not need to go to that because what is given is all of them are at same distance from the mobile.
Yeah,
So,
so basically my mobile would be at the center of the
right. So we
center.
could directly go for okay 1 by n into d by r the whole power n, right? Like we could go to that approximation directly.
Okay.
So basically n is given as 6. This will be equal to 1 by 6 into d by r. We could write it as root of 3n. Sorry, I shouldn't use n here. Maybe I should use L or something. So this will be equal to 1 by 6 into root of 3n the whole power n.
3.8.
Yeah, and this n is 3.8. This is equal to 10 dB. So it's
Which comes out to be 10.
yes. Yes. So we're going to substitute in this, n should be at least 3. 2.87 at least 3. Okay. Can I move on to the next question?
Yeah.
Consider a cellular system consisting of 180 users in a particular area. Each user makes an average of 1 call per hour. On average, each call lasts for 4 minutes. What is the total offered traffic in airlines? Total number of users we have. Each user makes an average of 1 call per hour and each call lasts about 4 minutes.
So it is 180 multiplied by 1 multiplied by 4.
Again, we'll have to check on the units. It's 1 call per hour and this is 4 minutes.
12 Erlangs.
Yes. So it's U into lambda into H. That's going to give us 12.
So,
Can I move on to the next question?
yes, ma'am.
What is the traffic intensity per channel for a cellular system with 25 channels and a blocking probability of 5%? So I want to give you some value. The blocking probability is 5%. So for 0.05 blocking probability and 25 channels, for 25 channels, the Erlang, based on the Erlang calculator, it is 19.95 Erlangs. Okay. So from the Erlang calculator, what we'll get is for 0.05 probability for 25 channels, I got the traffic intensity to be 19.95 Erlangs. So now what we have to find is the traffic intensity per channel.
Delta 0.798.
Yeah. So
Is
it
is it 19.95 divided by 25?
25, yes. So first you'll have to, since I couldn't go and show the calculator, I thought I'll just give the values. But this question will give an idea of how to solve these kind of problems. Okay. Assuming each user generates 0.15 SS. Okay. Assuming each user generates 0.15 Erlangs of traffic and the users are uniformly distributed over the geographical area covered by the cells, how many users can be supported for 5% blocking probability for 25 numbers of trunk channels in a block called cleared system? So we are going to get 133 users that can be supported. Okay. In the above question, if one channel is reserved for handoff purposes, how many users can be supported? Again, it's the same thing, but the traffic intensity is going to vary. Like for 24 channels and 0.05 blocking probability, if you see the chart, you're going to get 19 Erlangs. And we know that each user generates 0.15 Erlangs of traffic. So now the number of users supported will be 19 by 0.15, 126. The same thing, just you'll have to know how to look into the chart.
No, but here
Yes.
one channel goes right, 126 minus 5.
No,
Minus
user.
1.
One channel is reserved for handoff purposes. Previously we had 25 trunk channels, now we have only 24.
Okay.
Yeah. And now how many users can we support?
Okay.
Okay. Yes. We have a 7-cell reuse system and the average call lasts about 2 minutes. The blocking probability is 2%. Assume that every subscriber makes 1 call per hour on an average. Assume that block channels are cleared, so the blocking is described by Erlang B distribution. Yes, that also we know. If there are total 168 traffic channels per cell and 60-degree sectoring is employed by removing the omnidirectional antennas, what is the approximate reduction in the number of users per cell? What we are asked to find is, previously we'll be having omnidirectional antennas. In that time, how many users can we support? Now we are introducing a 60-degree sectoring. Now, what is the approximate reduction in the number of users per cell? I'll directly give the approach. First, what we found, I think it's now 168. So we have the capacity as 154 airlines. Then, what we are finding for omnidirectional antenna, how many users are we going to support? So lambda is given as one call per hour into each call lasts for 2 minutes. So 2 by 60, it's 1 by 30 airlines. So what is the total number of users we will support? 154 divided by 1 by 30. So 4635 users per cell we can support. But what we are doing sectorization. So it's no more a common pool. That sector's users, that antenna has to take care. Now, if we do sectorization, 168 divided by 6, approximately we are writing it as 28 channels. So, blocking probability of 0.02 and 28 channels per sector, I am getting the capacity to be 20.15. So, the total number of users what we can support is 20.15 divided by 1 by 30. So, 604.5 users per sector we can support. Into 6 sectors per cell, totally I'll be able to support maximum of 3627 users per cell. Now we find the loss of users, loss in the number of users. If a handoff occurs between two 4G base stations, it is called inter-rat handoff. True or false? When do we say that the handoff is inter-rat? That is, only when the handoff occurs between two base stations of different radio access. Say Wi-Fi is 4G, the other has to be 2G, 3G or 5G. Only if such kind of handoff happens, you say it to be inter-rat handoff.
No, but but it's the same 4G stations, right? So it is not inter-rat.
Yeah. So the answer is false. Okay. Which of the following is the most favorable action for a cellular system to take on a user whose RSSI is high and receive quality is low? The user is having good received signal strength, but the quality is low. What should we do for such a user?
That's quality is low. Quality is low.
We should be able to do both. So if the received quality is low, what does it imply is, see, the received signal strength is good, but the channel is bad. So what can we do? We can either go for an intra-cell handover within the sectors of a cell. Otherwise, we could do frequency hopping. That is, there could be a scenario wherein it's in the same frequency we are having a interference. So we could go for frequency hopping to get a better receive quality. So both A and C should help us. Next question. Software handoff is a procedure related to what? Yes. Software handoff means you tell it when you do a handoff in between sectors of the same cell. So basically it's an intra-cell handoff. Intersector, intra-cell, it's the same. Okay. We're almost nearing time, but I have 2 more questions. We'll just try to go faster. If a random variable x follows a log normal distribution such that the random variable y is log of x, which has a mean 0 and variance 1, what is the mean of x? We are given as y is log x. We have to find the mean of x. How can we find the mean of x? If y is log x, x can be written as e power y. So we have to find the expectation of x, which is expectation of e or e to the power of y. We know the mean and variance of y. Basically, it's a normal distribution. I'll go to the solution. We have to find expectation of e power y. We know that y is going to follow a normal distribution. So it's e power y into fy of y into dy. Directly if you integrate, we will be able to find the mean. Mean is root e. Is it okay? I'm moving on to the last question. Let's see the question, but you guys could try it at home, like offline. We'll see the answer for this question in the next session. A mobile phone receiver is operating at 2 gigahertz with a bandwidth of 200 kilohertz at 300 Kelvin. The noise figure is given as 6 dB. The receiver is present on the cell edge and a minimum of 4 dB SNR is required for a reliable communication. Consider log normal shadowing effects with sigma is equal to 6 dB. Given there is a maximum power constraint of 1 milliwatt that the base station can transmit, find the maximum radius of the cell for a 95% coverage probability. We have to assume a free space path loss model and Q of 1.644 is given as 0.05. You have to find the maximum radius of the cell for a 95% coverage probability. Can you all note down these data and give a try and come for the next session? The answer is 1.33 kilometers. So I will like you guys to solve it. Basically, the probability of outage is what we know. It's 0.05, which is probability of received power less than receiver sensitivity. You know the expression and values for received power, receiver sensitivity. Try to find what's D. What you should get is 1.33 kilometers. Try it.